All right, so the next type of recurrence relation that we're going to talk about is second order homogeneous recurrence relations. So this introduces some new terminology that we haven't really talked about, but I suppose we could have earlier. So first of all, the order of a recurrence relation just relates to how far back in time the recurrence relation references. Which is not to be confused with the number of previous time steps that are referenced, but just the furthest back that is referenced. So, for example, let's say that you've got x of n equals x of n minus 1 plus x of n minus 2. So that was our Fibonacci relation. So this is second order because the furthest back that the recurrence relation references is 2 time steps ago. So that's where this second thing comes from. But even if we just had something like x of n equals, I don't know, 1, well actually let me make that a 1/3. 1/3 x of n minus 2, that's still also second order, right? So in this one, we have 2 previous time steps referenced, but that's not why it's second order, right? It's because of this n minus 2. Similarly here, we've only got 1 previous time step referenced, but it's 2 time steps ago, and so that's why it's second order. So again, it just, the order refers to the furthest back in time that the recurrence relation goes. Also, this homogeneous part just means that if you get all of the x of n's or n minus 1 or whatever, if you get all of the x's on the same side of the equation, then whatever is left over on the right-hand side is 0. So in this general form that we're about to see, we've got all of the x's on the left, and then what remains is a 0. So just to compare with some of the previous stuff that we talked about, let me scroll all the way back up. Okay, so this geometric sequence, which we also called an exponential recurrence relation, it's first order, right, because we only go 1 time step back, or that's the furthest we go back. And then if we moved this Rx over to the left with this x, we would have 0 on the right-hand side, so it's homogeneous. So this is first order homogeneous. The one that we did here, it's also first order because, again, the furthest back we reference is 1 time step. If we moved this Rx over to the left, we have k on the right, and k is not necessarily 0, so this wouldn't be homogeneous. You could either call it non-homogeneous, or some people would even refer to it as heterogeneous, but usually people say non-homogeneous when k is not equal to 0. So those are just some examples. And also, I haven't made this explicit, but everything we've seen so far has also been a linear recurrence relation, just because it's linear in terms of all of the x's. So every x thus far that we've seen has the highest power of 1, and we're not multiplying x of n by x of n minus 1 or anything like that, because that would also give us essentially a power on x. So everything is linear. All right, so in the case where we've got second order homogeneous recurrence relations, we're looking at something with the general form as follows. So we've got some constant, we'll call it c sub 0 times x of n, plus c1, which is also a constant, times x of n minus 1, plus c2 is a constant times x of n minus 2 equal to 0. So again, this is why it's second order. And this is why it's homogeneous. Okay, so if you think about moving these 2 terms back over to the right-hand side, we'd have something like c naught x of n equals negative c1 x of n minus 1 minus c2 x of n minus 2. And so then if you divided both sides out by C naught, or C sub 0, you'd get negative C1 over C0 x of n minus 1 minus C2 over C0 x of n minus 2. So we've got this x of n, which is some constant times x of n minus 1 plus or minus another constant times x of n minus 2. Right, this is essentially plus some negative constant, which in the end could end up being positive anyway. But really we've just got something that looks kind of like r times x of n minus 1 plus s of x times x of n minus 2, right, where r and s are both constants. And so because of this piece, you know, we've got x of n equals r times x of n minus 1. That just by itself looks a lot like that exponential recurrence relation. And then similarly for the s of x, or s times x of n minus 2, if that were by itself, it would also look exponential in nature. So because of that behavior for this second order homogeneous recurrence relation, we might guess that the solution, or the closed form solution, looks really similar for the second order as it did for the first order exponential. So we're going to utilize that observation that we just made and then make a guess as to the solution type. So now that we've talked about that, I'm actually going to get rid of all of this stuff to give us a little bit more space. Okay, so let's guess that our solution x of n looks something like a times r to the n, just like it did before with that exponential recurrence relation. So if that's the solution, then when we plug in this solution into our equation, we should get a true statement. So we'll have C naught times x of n is a times r to the n plus C1. X of n minus 1 should be the same with just an n minus 1 here. So we'll have it times a r to the n minus 1. And then same thing with the x of n minus 2. We'll have C2 a r to the n minus 2. All of that's equal to 0. So I can clearly factor out an a from all three terms here. I can also factor out the lowest power of r from everything, which in this case is r to the n minus 2. So I'm going to go ahead and do that. So I'm left with C naught r squared plus C1 r plus C2. And now what we want to think about is whether we can divide both sides by this term. And the only time that we have to worry about that is if we're dividing by 0, because we know that that causes horrible things to happen. So if a were 0, notice that this solution would just be x of n equals 0, no matter what n is. And that will always be a solution to this second order homogeneous recurrence relation, because no matter what n is, you'd have 0 here, 0, 0. 3 zeros added together is 0. So that is a potential solution. It's the trivial solution. It's not very interesting. We know that it's a solution. So we're concerned with finding non-trivial solutions. So we're going to assume that a is not 0. We're also going to assume that r is not 0, because that would cause the same problem here, right? Regardless of what n is, x of n would be 0. So again, it's the trivial solution. It's not interesting. So for that reason, we're assuming both a and r are not equal to 0. So we'll go ahead and just make a note of that so that we can find any non-trivial solutions. We divide both sides now by this non-zero quantity. So no mathematical rules have been violated. And what we end up getting is some sort of quadratic polynomial, which is good news because we know that we can solve this in one of two ways. So we can either solve it by factoring, which is our favorite way to do it, or we can use the quadratic formula to solve. And in this case, the quadratic formula will give you that r is going to be equal to, let's see, negative linear coefficient plus or minus square root of the linear coefficient squared minus 4 times quadratic coefficient times the constant coefficient. So that's our negative b plus or minus square root of b squared minus 4 times a times c, all over 2a, which in this case is 2 times c naught. Okay, so as you know, when a quadratic polynomial is solved, you have essentially two roots of the polynomial, right? But there are a couple or a few different ways that those two roots can show up. So one possible case is that you've got distinct real roots, right? So you've got roots that look different, but they're both real numbers. So we'll say that one of them is called R1 and the other one is called R2. In that case, the general solution for the closed form solution of the second order homogeneous recurrence relation is x of n equals little a, which is just some constant that we haven't talked about before. So a times r1 to the nth power plus b, another constant that we haven't talked about yet, times r2 to the nth power. The constants little a and little b are determined by the initial conditions. Ah, what just happened? That was weird. So once you have this general form, you use your initial conditions to plug in for n and x, and then because it's second order, right, you're going to have two initial conditions. And so you'll have two equations and two unknowns, a and b, and so we know that we can solve those simultaneously to solve for a and b. So that's the first case that can happen when you solve that quadratic polynomial. Second thing that can happen is that you have repeated roots. So you have two roots, but they're both the same thing. So that's where r1 is equal to r2. So in this case, I'm just going to call it r overall. And in that case, the general solution is x of n equals some arbitrary constant a times r to the n plus arbitrary constant b times n times r to the n. And so this n here essentially just makes the, well, without getting into too much detail, it allows for more solutions that satisfy the original recurrence relation. So again, I don't want to go into too much detail about why that's there, but just for now, know that it works, and then that's how you handle a repeated root. So one of them you handle the same way as usual, and the other one you have some arbitrary constant times n times r to the n. And again, little a and little b are determined by the initial conditions. Third thing that can happen is that you have complex conjugate roots. So let's say that r1 is of the form alpha plus beta I, which is how our complex numbers usually look. And so then if the second root is the conjugate of that, it means we've got alpha minus beta I. And just as a reminder, with complex numbers represented in this form, alpha and beta are both real numbers, right? But one of them's attached to this complex variable I, or it's not, it's a complex constant actually, I, which makes the whole thing complex. All right, so if that's the case, again, without going into too much detail, what we're going to do is define, oh no, it's doing that crazy thing again, stop it, okay. Define R equals e to the alpha, and then we're going to let k1 be little a plus little b, where little a and little b are kind of serving the same purposes up here. K2 is going to be little a minus little b times I. And then your general solution looks like x of n, k1 r to the n times cosine of beta n, sorry that that's a little squished, plus k2 r to the n times sine of beta n. I'm going to rewrite this cosine part because it's bugging me. It will probably not turn out any better. Oh, it's already a little bit better. Okay, cool. So K1 and K2, again, are dependent on little a, little b, which were arbitrary, but those are, again, determined by the initial conditions. So one thing that's kind of interesting to note is that for this solution, compared to the other ones, so the other ones, were exponential in nature, just like our first example that wasn't the Fibonacci sequence. So, you've got this exponential piece, this exponential piece. Same thing here, you've got exponential and then a linear times an exponential, which still the exponential piece eventually wins out, either in terms of making this really small or really large. Yeah. Here you've got exponential times something sinusoidal in each piece, and so that causes some either growing oscillations or decaying oscillations or perfect oscillations depending on what the values of alpha and beta are. So these solution types are pretty interesting. And that's not something that I, again, want to go into too much detail about, but you can think about it and think about why that is the case just based on the setup of this general solution. All right, so let's go ahead and do a quick example for these, and then we'll be done. All right, so we want to find a closed form solution for the Fibonacci sequence as it was defined earlier. So we can probably just recall from memory that we had x of n equals x of n minus 1 plus x of n minus 2. And we know that x of 0 is 0, right, the 0th term in the sequence. And x of 1 is the first term in the sequence, which is 1. So this is second order. And it's homogeneous because if we move all of this stuff to the left-hand side, we'd have 0 on the right-hand side. So all we need to do is transform this guy into the corresponding quadratic polynomial. So I went ahead and moved the other x's to the left-hand side just so that we can see explicitly the homogeneous form that we have for this second order recurrence relation. And so remember we assumed that x was of the form a times r to the n, but we ended up factoring out an r to the n minus 2, so that what was left over was essentially this coefficient times r squared plus this guy's coefficient times r plus this guy's constant coefficient equals 0. And so if it helps you, you can work through the details of those again. But for me, I just go ahead and I know that this is going to turn into a quadratic polynomial with the same coefficients as the x's have. So we've got r squared minus r minus 1 set equal to 0. And this is what we call the characteristic polynomial for the recurrence relation. But again, that's not all that important. As long as you get that quadratic and we can solve for its roots, then we're good to go. So this does not look like it's factorable, unfortunately, so we're going to go ahead and use the quadratic equation to solve. So we're going to use negative b, which in this case is positive 1, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So that's 1 plus or minus square root of 1 plus 4 all over 2. So this is 1 plus or minus root 5 over 2. So just because there's this radical in there, as well as the plus or minus, don't think that these are complex, right? There's no I. So these are distinct real roots. We've got r1 equals 1 plus root 5 over 2. r2 equals 1 minus root 5 over 2. The general form of our solution should look like a times 1 plus root 5 over 2 to the n plus b times 1 minus root 5 over 2 to the n. We can use our initial conditions to solve for little a and little b. So when n was equal to 0, x was equal to 0. So that gives us the following equation. 0 equals a times anything to the 0 power, well, any finite number to the 0 power is 1. Same thing here. So this tells us that a plus b is equal to 0. That's our first in the system of equations that we're going to deal with. And then when n is equal to 1, we have x equal to 1. So that gives us 1 equals a times 1 plus root 5 over 2 to the first power, which is just itself, and then plus b times 1 plus root 5 over, whoops, that was a minus. Sorry about that. And that one pretty much is as simple as it's going to get. So I'll just say ditto there. So now if we solve that system of equations, what we should get is that a is equal to 1 over root 5 and b equals negative 1 over root 5. And I'm sort of omitting those details, but you can confirm that for yourself in a few minutes or on your own. Just make sure that once you do that algebra, you know, this equation with this equation, it's a little ugly just because of those radicals, but it's really not too bad. But you do end up getting those coefficients. So we could plug these in for x of n and have our specific solution for the Fibonacci sequence. Alright, so that's it for this video. Please let me know if you have any questions, and I'll see you next time.